Good morning and welcome to lesson 2 where we look at algorithm and time complexity. So here in lesson 2 video we're going to be looking at focus more on the cost and time complexity. Okay, so we need to understand time complexity. So now time complexity has to do with a major. So time complexity has to do with a measure of the computational time an algorithm takes to complete as a function of the size of the input. And some of the the types of time complexities we will look at here is the constant time complexity, the logarithm time complexity, the linear rhythm time complexity, the quadratic time complexity, and I think, and then exponential time complexity. So that's what we're going to be looking at in these lessons, in this lesson 2 video, but this is lesson 2A, which will focus more on the constant time complexity. So we need to understand why time complexity is important, right? So the first one is scalability. It shows how an algorithm performance will scale with increasing input size. Then optimization. It helps identify which algorithm is better suited for a problem, especially when large data sets are involved. Right? So there's a notation for this time complexity, which are the asymptotic notations, right? So one of them is the big O notation, right? So big O notation basically focus on the worst case scenario. So we're going to be learning some of the asymptotic notations where we look at the worst case, the which is the big O, then the average case, then the worst average and the best case. We're going to be looking at that when we're looking at time complexity, right? So now the types of time complexity. The types of time complexity, the first one we have is the constant time complexity, where you have the order of, which is the big O. There you can see the O, order of one. So this algorithm takes the same amount of time regardless of the input size. So we're going to be learning this. We also have other type complexities which we'll be looking at. And this will be in lesson 2A, and this the linear time complexity, which is ON, the time grows proportionally, directly proportionate to the input size. We'll cover this linear time, and we'll cover this and the quadratic time complexity in our lesson 2B. Then we will cover logarithm time complexity and the logarithm time complexity and the linear rhythmic time complexity in our lesson 2C. And then the last one in our lesson 2D, we'll look at the exponential time complexity, where the time doubles with every additional input size, which is O2N, where a good example we'll look at in this one is the Torah of Hanoi, right? So in this one here, the good example we'll look at here is a merge sort and a quick sort. So it's a combination of linear and logarithm time complexity, right? So let's move on to the constant. Okay, we also have, like I said, we have these asymptotic notations. You can see that the big O is the worst case scenario and is most commonly used in algorithm analysis. Then we have the big theta, which describes the exact growth rate and is used when the algorithm has um, consistent performance. Mainly, this has to do with the average case scenario, and the big omega has to do with the best case scenario. It gives a lower limit for the algorithm performance. So basically, this focus more on the worst case scenario. It's more commonly used in algorithm analysis, and this is what we're going to be using, right? More. But not that we'll not explain the worst case and the best case scenario for each of our algorithms, right? So now, what is constant time complexity? Constant time complexity means that no matter how big your input is, the operation always take the same amount of time. No matter how big your input is, the operation always take the same amount of time. So think of it as an action that happens in one step, regardless how much data you have. Now, imagine you are in a room with 1,000 light switches, one for each light in a stadium. Now you're asked to turn on one specific light, like the one for row 5, column 3. So what do? You walk straight to the switch and flip it. It doesn't matter if the room has 10 switches, 100 switches, or 1000 switches. You only perform one action. So this is a constant time complexity because the time it takes you to turn on that one light does not depend on the total number of these. So let's use a good example. Now let's assume that we have a variable called x, or let's assume that we have let's assume that we have a variable called arrow. So this array here is holding a list, right? So this is a list which is noted as a square bracket. So now this list has an items of integer data type of 4, 6, 7, 8, right? 10, 12. Okay, now let's assume that um, pick in, we want to pick a particular value or a particular item in this list. Remember that this is a collection of items, right? And each of these items are located in their indexes, right? So this is a list, and then you can see that 4 is located in index 0, 6 is located, let me do it very well so we'll understand what we're trying to do. So let me use so this is index 1. Let's 4 is in index 1, 4 is in index 0, 6 is index 1, 7 is index 2, 8 index 3, 10 index 4, and 13 index 5. So this one is located in index 0, and this item is located in index 1, and this one is located in index 2, and this 8 is located in index 3, and 10 is located in index 4, and 13 is located in index 5. So now let's assume that we want to access a value because computer is dummy, right? And we have already passed in this list, and this variable array is holding this list. And then so well they want computer to access to return a value located in their indexes, right? So let me just use I want to use print because I'll be using a Python format way of writing this algorithm and then explaining how it works, right? So that we all will understand how this algorithm works here. So now if I'm printing this array, then a square bracket like this. So I'll put their index, let's put index 0. So what this does is it will print out 4. It will print 4 because 4 is located in index 0. So now this is an example of a constant time complexity. It means that no matter the index I'm trying to fetch a value from, right? So it's the same amount of time it will take. It's the same amount of time it will take. So the computer will print 4. So even if I'm printing from index 5, right? So the computer will print out 13, right? So this is a very good example of a constant time complexity. This is a good example of a constant time complexity. Now, what constant time complexity is not, right? So what constant time complexity is not is when I'm trying to loop this array. Let's assume for I down to the range from I to, or let's assume from I is equal to 0 to the length of this array. So this is not constant time complexity, right? because the length of the array grows. So let's assuming that the length of the array here, because what this length of the array does is, this is the array, right? So the length of the array is the total items we have here, which is 1, 2, 3, 4, 5, 6. So automatically what we have here is 6, right? From I down to this to 6. It means that you are linearly counting 1, 2, 3, 4, 5, 6. So this is not constant time complexity because you are looping through linearly. So this becomes a linear time, which we're going to be learning in our next video. So this is not constant time complexity, but this is a constant time complexity because we are assessing it directly. You are assessing these numbers directly. Another good example of constant time complexity is when we have a function like a is storing like a variable called a which holds 4 and a variable called b which holds 5, and you're saying c should be a plus b, right? And then you are printing c. So you are printing c. So this is another example of a constant time complexity, right? Is another time because even if you put in 4,000 here and you put in you put in 5,000 here, so it returns the same. It's on the same C, right? So it's not actually looping through these to compare anything, right? So anything that has to do with the linear comparison or looping is not constant time complexity, right? So this is a good example. So we'll just use just one example here because of time and because so you can see how constant time complexity is, right? So constant time complexity is fast. We're going to be learning more of constant time complexity where we're looking at hash tables, right? You see how it works. So remember that the loops that's not constant time complexity is not constant time complexity, right? So you can see what this example is. You can see, imagine you are in a room with 1,000 light switches, one for each light in a stadium. So you are asked to turn on one light, one specific light, like one row for one row 5 column 3. You can see you just go directly and then switch it on, right? So that is how this works also. So when you have a collection of items like these and you just want to access a value located in this particular index, right? If I look at any particular index, that is why you just go there and pick it. So if you want to delete these, just you can see, right? So that is how constant time complexity work. The other examples like the addition, subtraction, division, and also assigning value to a variable where we have x and you want to assign 5, or you want to change the 5. We have also can have x also, and you want to change that value to 4. So these constant time complexity. So that is how it works. So I believe you understand constant time complexity. If you have any question, feel free to ask me. I'm always here to answer you. And then if you need more examples, you can be able to contact me and then I will teach you. Thank you and God bless you.